Okay, thank you, Shaka. So my project work that I did here was about the experimental demonstration of non-stateful logic with silicon oxide based VCM RRAM cells. So a little bit about the background or the motivation. So as we all know, probably Moore's law, that the number of transistors on a chip doubles every 2 years. But as we can see here at the trend line, that we now reach a state of the transistor size of 1 to 5 nanometers, and that is very close to the atomic scale. So we have to think, how can we overcome this limit? How can we find new technologies? And what comes next? So far, we always use for computers, we use the von Neumann architecture. So we have a separate processing and memory unit, and between them, we have to have data transfer. But what's the problem with this? This data transfer has always have to be a minimum, and you can't reduce it from a certain point even more. So the solution for this would be that we have now a memory unit where you can also perform logic in the memory. And for that, we can use memristors, and they combine characteristics of a memory and also a resistor. So here you can then store a state through a resistance, a high resistor state and a low resistor state. So based on that, now to the structure of my talk today. So first, I will present the theoretical background, where I present what you have to know for the later measurements and results. Then I go over to the experiments and talk about the sample and the setup. And then in the end, I will discuss my results. So as I mentioned earlier, you have the memristor and you have 2 states, and you can switch between them. And the switching is based on different mechanisms based on the material properties. And the most famous one of this list is, for example, the electrochemical metallization effect called ECM, then the valence change memory effect VCM, and also phase change memory effect PCM. In this work, we'll deal with VCM cells, and they are redox based and they switch bipolar. So what does it mean, bipolar switching? We can distinguish between unipolar and bipolar switching, and here is the characteristic of unipolar switching shown. So we have the switching is dependent on the absolute value of the voltage. So we can see that on both voltage sides, we have the same process happening at low voltage, always a reset, and at high voltages, always a set process. In comparison to that, we have the bipolar switching. Here, the switching is dependent on the voltage polarity. So we have defined that the positive voltage leads to a set process, negative voltage leads to a reset process. And the VCM, as I mentioned, are bipolar switching devices. So a bit more about now the actual switching cycle. Here you can see the structure. It's the metal insulator metal structure of the cell, and you have an active electrode, an insulator layer, and an ohmic electrode. And in the insulator layer, after forming step, there's a conducting filament consisting of a plug and a disk area. And the plug area, this is conductive, and the disk area is non-conductive. And in a process now called set-reset, we can change the conductance of the disk area so that the conductance of the cell also changes. And how's that working? So we have here the EV characteristics, so how the current changes with changing voltages. And after a forming step, we start in the off state. Here you can see there are no oxygen vacancies in the disk area. Then we perform a set process where the oxygen vacancies move inside the disk area, and that leads to an on state where the resistance is low, and it's a low resistance state. We can reverse this process by applying the opposite voltage polarity so that the oxygen vacancies move back out of the disk area, and we're again in the off state. Now we have a look a bit further to the oxygen vacancy movement. We can see here that if you apply the voltages for a set, then the oxygen atoms move towards the ohmic electrode and they leave a vacancy behind. If that happens more often, you can observe a total drift of vacancies towards the negative voltage. If you consider now the oxygen vacancy concentration in the off state, you can see that here in the disk area, the concentration is very low. So that means that here the potential wall is very broad. So the resistance is higher. If you now perform a set and are after that in the on state, you can see here that in the disk area, the concentration of vacancies is very high. So the potential wall decreases massively and the resistance gets low. You can reverse this with the reset so that the oxygen atoms move back from the ohmic electrode to the insulator layer, and effective drift of the vacancies is to the ohmic electrode. Also here you can see then that the concentration of the vacancies decreases again and the potential wall increases. As we saw in the previous slide, the switching is dependent on the voltage, but also massively on the time. So we have here the voltage time dilemma. That means that if you change the voltage only by a little bit, the required time that the voltage has to be applied changes over an order of magnitude even more. So the pulse time is a very important parameter, and you always have to try to find a compromise between short pulse times and low voltages. Even though ReRAM devices have the potential of ultra-fast switching and also very power efficient operating, they unfortunately suffer from several reliability issues. So the first one is shown here, that's variability, and in particular cycle-to-cycle variability. So here the measurement was repeated for several cycles, and as you can see in the result, it shows a different behavior in each cycle, even though the measurement parameters were exactly the same. If you're wondering what the red graph here is, that was just a measurement with another current compliance, but you can also see here the cycle-to-cycle variability. Then the next kind of variability is cell-to-cell. So that means that each cell also has a different behavior, even though also the layers are completely the same. And that we can see here, this was measured with 48 cells in total, that there's a range of the LRS and HRS state over several, over a broader distribution of the resistance. What can also happen is that writing failure occurs. So that means you have a cell, for example, in an HRS state, so in the off state, you want to perform a set process. You apply the corresponding voltages, but the cell just doesn't switch and stays in the HRS. This you can see here, the red ones, their writing failures occurred. Also, there's read noise. That means that you never measure one straight line when you measure the current. You always have some variations, and of course that decreases the quality of your end measurement. What also happens is a retention, also called state drift. So when you program a cell into a specific state and wait a long time and then measure it again, then the state drifted a bit. You can increase that by increasing the temperature so that you can evaluate how it happens, like how much time it happens for which state drift. And the last one is the endurance. That means that a cell can switch for infinite cycles. You always have a limited amount of switching cycles, and afterwards it can't switch again. So here you can see a device that was ultra high endurance. So also even after 10 to the power of 10 cycles, you can see only that the HRS decreases a bit, but usually for ReRAM devices, the endurance lays in the magnitude of 10 to the power of 6 to 10 to the power of 9. Okay, now that we learned about the general switching processes, we can now go on to the application for logic in memory. So the memristor can be used to store a state through a resistance, and we can define two states. We have the high resistive state as logical 0 and the low resistive state as logical 1. And if we want to switch between them, we apply voltages. And the convention here is that wherever this black bar is, a positive voltage that is applied on this side would lead to a set process. And the other way around, if you apply the positive voltage on this side, on the other side, the cell effectively sees a negative voltage and the reset crossover happens. So you can differentiate between different logic types. You have first the stateful logic, and here one state variable presents the memory and also the logic operation. So you have, for example, the resistance as input and output, and also as the stored value. So here is the example of a magic circuit. The non-stateful logic has then different representations of the memory and logic operation. So you can, for example, have the voltage as input-output, but the stored value as resistance. And this work in particular will deal with two non-stateful logic techniques that I will explain now, and they will be shown experimentally afterwards. So the first logic techniques that this work is dealing with is the complete Boolean logic with 1T1R. You need this stack for it. It's a 1T1R. So you have here the cell with including the top electrode, the insulator layer, and the bottom electrode, and then it is placed on a transistor. And if you refer further to the equivalent circuit, it looks like this. So you have the top electrode, here the bar, so that means if you apply a positive voltage at the top electrode, a set process happens. You have here I, that stands for the initial resistance of the memristor. You have G as the gate of the transistor and the bottom electrode. And if you now want to perform the 16 Boolean function, Wang et al. Proposed this table so that you define 4 input parameters that are shown in the equivalent circuit, corresponding to either 0, 1, or a variable of P and Q of a 2 input gate. And how does it work? So we consider now the end function, for example. We can see then that G should equal P, as you see here. Then the top electrode should equal Q. The bottom electrode should equal 0, and the initial state should be 0, so in the high resistance state. Now, if we have all 4 combinations of P and Q, we can go through it. So we apply first case. So we apply a 1 at the top electrode, we have 0 as the bottom electrode, the transistor is open because it's 1, and the memristor is in an initial state of 0. And what can happen then? We have a voltage difference between top and bottom electrode, a positive voltage at the top electrode, so a set process is possible. It also is supported because the transistor is open and the cell is in a high resistive state, so the cell can perform a set. And that's also what happens. So you perform a set process, and then you have the memristor change from 0 to 1, and then the 1 is the red output. And also you should have here an output of 1 for the end operation. So that's how it's realized. If we then consider the second case, we see here that the top electrode changed to 0. So now we don't have a voltage difference between top and bottom electrode. So no set process can happen now. So the cell stays constant at 0 and the output is 0. In the third case, we do have a voltage difference between top and bottom electrode, but here the transistor is closed. So also here the cell doesn't switch, stays in the HRS, and the output is 0. And in the last case now, everything is 0. There's neither a voltage difference nor the transistor is open, so it also has to stay constant. If we now consider all different combinations that are possible with 4 inputs, we can see we get this table here, and then we can for each case we can calculate the difference between top and bottom electrode, and it can be either 0, so there's no difference, or +1 that corresponds to a set process, or -1 that corresponds to a reset process. But not only the difference between top and bottom electrode is important, but also if the transistor is open and in which state the memristor is initially. So we can see here if the process is possible. So it's not possible when the transistor is closed. So here in these 4 cases, 11 to 14, the transistor is, the G is 0, so the transistor is closed, and the processes can't happen. For the cases 3 to 6, the transistor is open, but it also can't always happen because, for example, in case 3, the cell is already in a low resistor state. So a set process wouldn't change the resistance of the state, and the set can't happen. And the same also counts for the reset here, because here the initial resistance is already 0. Now what we want to do experimentally. So I chose 6 of the Boolean functions because they are very important for different applications. So it's the not P, not Q, or, and, NIMP, and XOR function. And then I filled in all the cases for P and Q for each logical function. And if we now compare them to the table of the input combinations, then we can see, for example, this case equals case 14. And then we can look into the table. Okay, a reset might happen, but it can't happen because the transistor is closed. So the cell stays in the initial state of 0, and the output is also 0. But if we, for example, see now this case, we can see that here there's a difference of +1, so a set can happen. The transistor is open, and the cell is initially in a high resistor state. So the switching should happen, and the initial resistance changes from 0 to 1 as an output. And that's what I will show experimentally, that each of the cases of each logical function is working. And all of them together, if you sum up all the cases that are considered here, it includes the cases 3 to 8 and 11 to 16 of the table. So all the others can be considered as not really critical because there's no voltage difference. And therefore, with these 6 logical functions, you can demonstrate the whole Boolean logic table. So now I go over to the second logic technique. It's called scouting logic. How does that work? So we need this shown circuit. We have 2 memristors, those are the inputs, and we apply a read voltage simultaneously at both of them, and then measure the resulting current and compare it to a reference current. And to make it more clear, we have here a just regular read process. We have one cell in a specific state, and then we measure the current and can say then if the state is in an LRS or HRS, depending on the current. So for example, we have here the cell in a high resistive state. We measure the current. Okay, the current is low. So we can say the cell is in a logical state of 0. If the current is high, we can say the output is 1 because the current is high. But we only can do that because somewhere we place this reference current where we say, okay, each current below the reference current equals 0, and each current higher than this equals 1. And exactly the same we will do now for 2 cells, but here we have now different input combinations. So we can have, for example, both cells in the HRS, both cells are 0, so it's the case 0, 0, and we measure a low current. If both cells are in LRS, the current is very high, and if each one of the cells is one is in LRS, one is in HRS, we have a median current. And if we want to now realize an end function, we know that only the input of 1, 1 should lead to an output of 1. So we place now the reference current at this place, so that only that we say the currents higher than this reference current is 1, and all the rest is 0. So therefore, we realize an end function. We can also do the same with the OR function, but here we place the reference current between 0, 0 and 1, 0, 0, 1. So we have that only the input of 0, 0 leads to an output of 0. And the third one, the third function with the scouting logic is an XOR function. Here we want that the inputs of 0, 0 and 1, 1 lead to an output of 0. So we have to place 2 reference currents so that the currents below reference current 1 and higher than reference current 2 lead to an output of 0. And in reality, these shown current bars are not really bars. They are actually Gaussian distribution because of the variability of the cell and also of the cycle-to-cycle variability. So what I will do in this work now is to show experimentally how the currents are distributed for each input state, and then place a reference current if possible, or say, okay, there's an overlap of the states, so there's no placing of the reference current possible. Okay, that was the theoretical background. And now I will go over to the experimental part and starting with the sample. So the sample was of the manufacturer Weebit Nano in an 8x8 crossbar configuration. And here you can see the SEM image of the stack. And the stack is a silicon oxide layer sandwiched between titanium nitride as bottom electrode and titanium as top electrode. And here on the right, you can see a picture of the full sample. And as I mentioned earlier, a set process happens for this with a positive voltage applied at the top electrode and a reset process for a positive voltage at the bottom electrode. Here you can see the ideal measurement parameters given from the manufacturer Weebit Nano, but I will also do the characterization experimentally myself. Here you can see the 1T1R crossbar array. You can see that each cell is connected to a select line and a bit line, and to open one of those, the select line and bit line have to have the same index. It's also needed to open, if you want, for example, to choose this cell, that you open the word line to open the transistor, and then you have selected this one cell. The top electrode diameter is 120 nanometers, and the transistor width is 5,900 nanometers. And what you can also see here is the transistor characteristic. That means the measured current for different drain voltages for different gate voltages. Now I go over to the measurement setup. This shows the probe station that was used for all the measurements, and here's the sample that's placed inside of it. And it was measured with a measurement device of called B1500A. And the connections on the sample works like this. You have four shown needles here as a scheme, and they are connected then to each one channel of the B1500, and then you can apply voltage pulses as you want. Another possibility is to use WGFMU channels, and then you can connect also RSU in the middle, so you can switch between the WGFMUs and SMU channels. So what's the first thing that I did? So I first want to know, how does the cell behave? So I performed sweep measurements. Sweep is a voltage increase in a stair shape. And for that, I was using SMU connection. And I connected SMU 1 to 4 to the top electrode, bottom electrode, word line, and bulk. And the pulse width are in the order of milliseconds of the voltage sweeps. In the second step, I then performed voltage pulses to also see how the cell behaves for pulses, because in the actual application of logic, you can't use sweeps because that would be much too slow and much too much power consumption. So the difference between a pulse and a sweep is that at a pulse, the voltage drops to 0 volt between each pulse. And for that, I then use WGFMU channels. Again, 1 to 4 for top electrode, bottom electrode, word line, and bulk. And here I had to change the channels because for the pulses I need much faster channels. So the WGFMUs are in the nanosecond range. So these were used for the pulses. If you then look at the array connection for the cell characterization, you apply a positive voltage at the top electrode here, as it is the select line, and you have the bit line grounded, so the top electrode grounded, and you open one transistor, so you select the cell and perform a set process. For the reset, you just do it the opposite, so you change bit line and select line so that now the positive voltage is applied at the bit line. A read process can be done by doing the same configuration as for the set, but just using very much lower voltages. For the 1T1R logic, you need the 4 inputs. So you have top electrode, bottom electrode, the G and I, and then you apply for each case that you want to perform, you apply it corresponding to what the table says. For the scouting logic, you then need to connect 2 cells in parallel. So what do? You apply at one select line a read voltage and then open 2 transistors so that you have here a parallel connection of those 2 cells. Okay, now I'm going over to the results and discussion. So the voltage sweeps for one cell. They, you can see here the results of 100 cycles, and they were measured with this given measurement parameters. And what you can see here in the first place, that there's a sufficient gap between the currents before and after the set. So here is the set process happening, here's the reset process happening, and at a voltage of 0.1 volt, you can then extract the resistances, and here is a sufficient gap. So that means that the processes were successful. But what you can also see here, that there's a wide range of voltages that lead to the set process. So that means you have a broad, a large cycle-to-cycle variability, and that means for the application that you have to use a general voltage of 1. Like it ranges from 0.7 to 1.45 volt, and then you have to choose a voltage of 1.5 to make sure that the cell sets for each cycle reliable. You also see the variability here, but it's much slower, much lower for the reset. If we then go over to comparing multiple cells, doing exactly the same measurements, each 100 cycles, you can see here the result of the mean curves of those cells. And here then you can see the cell-to-cell variability, which has to be taken into consideration for later applications. What you can also do is extract the resistances for all the 100 cycles for all the cells, and then plot it all together in this graph. And you can see here that the distributions of HRS and LRS are extended. So you have, of course, the variabilities here, and you have a mean resistance ratio of the HRS and LRS of 19.4. This can be considered as a good result because for RRAM devices, it is above 10 is considered as a good result for this. Here is also a needed gap. So you can always say that there's no overlap between the states. You have some outliers here, for example, this point and this point, but still here the ratio is 1.3. So there's still a distinction that can be made between those points. Now, after the characterization with sweeps, I go over to the pulse characterization. So I measured 6 different voltages with 3 different pulse times. So and then calculated the ratio of HRS and LRS. And what you can see, what you would expect is that with rising voltage and rising time, that also the ratio rises. But here are the measured results. So if you consider the voltage in the first part of the graph, then you can see that the voltage, that the ratio rises with increasing voltage, but at some point when it reaches a threshold voltage, for example, in this case, then an increase of the voltage doesn't increase the resistance anymore, the ratio anymore. So that means that that is caused because you have a relatively stable state of an LRS, and the cell always wants to switch into this LRS state. So if you once reach a voltage where this can happen, also a further increase of the voltage doesn't change this stable state. Yes, and also for the pulse width, you can see that from 100 nanoseconds to 1 microsecond, the results getting better, so that you need less voltage for the same ratio. But in the step from 1 microsecond to 10 microseconds, you can see that the results actually get a bit worse. So this might be explained that there are some interfering phenomena during the measurement, or that there are some problems with the measurement device, but this has to be investigated further. So from this graph, you can then extract the measurement parameters for the later logic operation. And here the best pair of parameters with this one. So for the set, voltage of 1.2 was chosen and the time of 1 microsecond. But in the later measurement, it showed that not for all cells 1.2 volts were sufficient. So I increased the voltage by 0.1 volt to make sure that all of them switch. The same can then be done with the reset. And here you can see that the voltage dependency is more like what you would expect, because here also the HRS distribution is much higher, so you don't have this very narrow stable state of the HRS. You have much more opportunities, so you can switch into different states. But also here you can see that the pulse width at some point it decreased the result. So here the reset parameters that can be extracted from this are 1.6 volt and the pulse time also 1 microsecond. So this one was the best pair. And from this then we get this table of the measurement parameters, and they count for all the later logic measurements. So here are the results for the logic. First is the 1T1R logic. Here are all the investigated 6 cases of the Boolean functions. And if you now look at the not P gate, for example, you can see that the input combination is plotted on the x-axis, and it's a not P gate, so you have here the P always as 1, 1, 0, 0. And because it's not P, you want the output of 0, 0, 1, 1. And the initial state of the memristor was already 0, 0, 1, 1, and it didn't change, so the output was also correct, and the whole gate was considered as working. If you look at the AND gate here, you can see that in the first case, in the input combination 1, 1, there's a switch from the high resistor state, the initial one, to the low resistor state. And here you can also see a relatively broad distribution of the HRS region, but still a gap between HRS and LRS. So also this is considered as working. And if you look at all the other gates, also it's always the expected result. If you look a bit closer to the non-switching cases, so where the initial and output state stay the same, they are all plotted here over the cycles. And as you can see, the resistance stays very constant for all cases except one. And this is case 6. This is this case. It shows slight variations, and this is caused by HRS instabilities, because when you look at the table, there the transistor is open, the voltage difference is -1, so a reset can happen, but only the state is the resistance is already 0. So the voltages should allow a process, but it's already 0, so there are some variations still, because there are always HRS instability. Going over now to the results from the scouting logic. So what you can see here is first the input combination for the different combinations. Here for the read it's only one number, for the other ones it's 2 numbers, because they're 2 inputs. This yellow distribution, this yellow histogram shows the current distribution of the counts. And this is the CDF plot of the current distribution. The green gap shows where no current was counted, so that this is the range where you could place the reference current. And as you can see in all of the plots, there's always a place for the reference current, so you can reliably place the reference current, and these are the values that could be extracted for the operation. But what you can also see here is that the distribution is as expected, has a Gaussian shape. So you have the cycle-to-cycle variability. Here there were 100 cycles measured. And also the cell-to-cell variability, because in this cases, you have different LRS states of different cells. So in the 1,0 case, the first cell is in the LRS, in the 0,1 case, the second cell is in the LRS. So this shift shows the variability. Now about the challenges of this work. So I have the 1T1R configuration, but this allows only very limited logic techniques, because you can't connect two cells in series, and the parallel connection is only working like this, that you need to select the same indices for select line and bit line, and then open two word lines, so that you have then this connection. But the problem with this is that you can't apply different voltages at both cells. You can only apply one voltage at the select line and one voltage at the bit line, so the voltage difference at both cells is always the same. A solution for this would be another design. So for example, a pseudo crossbar array. This is shown here. So here you have two select lines actually selected, and one bit line, and then also one word line. So then the connection is like this, and you can apply two different voltages at the select line, and there's no there at both sides there's a different voltage difference. Another, of course, very big issue is the RRAM reliability, because it can cause problems in the correct logical output. So as I showed you, the variability plays a very important role, because for the scouting logic, it can lead to an overlap of the different input combinations. And also for the 1T1R logic, the states shouldn't overlap. And also, of course, writing failures that also happen during the measurements, they would also, of course, lead to a wrong result. So in general, the measurement setup can be optimized to realize shorter pulses, more exact measurements, and also that you measure less noise and improve the quality of your measurement. So as a conclusion, in this work, I characterized the silicon oxide-based VCM cells in a 1T1R arrangement, first with sweeps and then with pulses, and found out that the cells are suiting for specific non-stateful logic techniques. And then I demonstrated two logic techniques, first the 1T1R logic, and second the scouting logic, and they all showed correct logical output. However, it can be potentially endangered if the RRAM reliability issues get more severe. So, and in the end, you have challenges due to 1T1R configuration that was used, and also due to the RRAM reliability issues. As an outlook for the near future, there have to be more measurements taken so that you can extract more exact values for the logical operations. The manufacturer has to improve the cells itself so that there's less voltage variations and less variability to make it more reliable. And you can use the different 1T1R configurations. And for the far future, of course, the goal would be to revolutionize the way a computer is working with non-von Neumann technology. Do you have any questions?
Very nice talk. Enjoyed it. Did you design the fabricated sample, or was it some off the shelf?
It was off the shelf. It was manufactured from Weebit Nano, so not in the house here.
Okay. And you also mentioned that there should be some different design of the 1T1R configuration. So what are the potential problems that can arise from using that specific design? Because if it's 100% better, then I would assume that they already use.
So I guess the used 1T1R arrangement, it is very good scalable. So it is very common, very easy to manufacture, and you also avoid other sneak path currents because you really can only connect this one column, and the rest of the cells is completely untouched.